morning, good afternoon, good evening, whatever the case may be. We are back in better than ever, and today we're talking about the sine rule. We got the Ace of Base going here with their epic song. Wonder what the name of it is. Wait for it. It's coming along. Here it comes. That's right. I saw the sign and it opened up my eyes. Yeah, it's a must for the sine rule. Let's get to it, shall we? Alrighty then. Sine rule, here it is, really. I'm not going to read this to you. It is a relationship among the angles and sides of any triangle. And the proof is really, really nice. We already proved in the first section that the area of any triangle is given by 1/2 BC sine A, 1/2 AC sine B, 1/2 AB sine C. This is the one that is on our formula booklet if you look right down here. But it's really like a pattern like we talked about in class. It's 1/2 of the product of the sides that form the angle, and we take the sine of that angle. Okay, so all of those are equal because they represent the area of an individual triangle. This particular triangle, let's say. And if we divide everything by 1/2 and simplify a bit, we end up with this relationship. So that's where the sine law, the sine rule comes from. And it doesn't matter if the angle is on top or the side length. Doesn't matter because it's a ratio, it's a proportion. So if we just have the side lengths on top and the sines of the corresponding angles on the bottom, it is just fine. In fact, that's how our formula booklet has it. Okay, so let's try it. Find the length of AC correct to 2 decimal places. So we're going to use the law of sines here. I always say the law of sines. It's the sine rule. I was taught the law of sines. And so we're going to say, in this case, I can say that I have 12 in this angle opposite of C, and I have 58 degrees in the side of opposite of B, which is AC. I'm just going to label it little b. So I'm going to say that B over sine 58 is equal to 12 over sine 39. So this is just a proportion, okay, or it's an equation. I'm going to multiply both sides by sine 58 times sine 58. And so cancel, bam, B is equal to 12 sine 58 degrees over sine of 39 degrees. And then I'll crank that on my calculator. Please notice that I didn't find the sine of 58 and the sine of 39 and write them in as decimal approximations. Do not estimate, do not round until your final answer. So I need to take 12 sine 58 and divide it by sine 39. So I'm going to use the fraction bar and type in 12 sine parentheses 58. My calculator is in degrees. I see it right here, so I don't have to put the degree symbol. If I did, it is located right there, and I would just crank it in. I can put it in there now. It won't affect it, but I'll leave it out. Over the sine of, I forget the angle already, it is 39. Bam, and I get 16.17. So I can say that it's approximately equal to, let's see, approximately equal to 16.2. And that's centimeters. Okay, easy peasy. But unfortunately, with the law of sines, there's a couple of hiccups. That's what makes the law of cosines better, as there aren't any hiccups when you use the law of cosines. But with the law of sines, there are some exceptions that we have to be keenly aware of. And that's because in quadrants 1 and 2, if you remember, in both quadrants, sine is positive. Because remember, sine is corresponds with your y-coordinate, and sine is positive in quadrants 1 and 2. For example, if the sine of theta equals the square root of 3 over 2, that could be at 60 degrees, or it could be at 120 degrees. The ordered pairs here on our unit circle are 1/2 root 3 over 2 and negative 1/2 root 3 over 2. So I have two possible angles. So we have to be careful. And here's the situations. There's 4 possible situations. Could be, I have 2 here. If I have little c equal to 10 centimeters, so that's the side opposite big C, and little a equal to 6 centimeters, then and angle A is equal to 30 centimeters, then C could turn out to be either about 56 degrees or 123 degrees. Okay, and you can see that how it could be 6 centimeters here, or it could be 6 centimeters here, having an acute angle or an obtuse angle right there. And it's always going to be 180 minus that, because if you think about this angle, it's going to be 180 minus the acute angle. So this is 60 degrees, right? And if I rotate over here, this is 120 degrees, right? So the sine of 60 degrees is equal to the sine of 120 degrees. We've established that. They're both root 3 over 2. And the sine of 60 degrees is also equal to the sine of 180 minus 120, which turns out to be, and will always be the case, the same as the first one. That's true of any angle, like sine of 30 degrees is equal to the sine, if this is 150, the sine of 180 minus 150, which is the sine of 30 degrees. And we already know that sine of 150 and sine of 30 are the same. So that's called the ambiguous case, where we always have to check. It also could be that it's a right angle, and the angle is 90 degrees. So if we get a 90-degree angle, we know that's the only possibility. It also could be that there are no solutions, that the dimensions are such that the third length is too short, and we can't form a triangle with the given information. Or it could be that there is only one solution. And we'll go through how you check that, each of these. But the moral of the story is we have to be very careful with the law of sines. All right, so find the measure of angle C in a triangle ABC, and they give us the measurements. So let's go ahead and draw that real quick. Doesn't matter. Just know that you're probably not going to draw it to scale. Okay, so we're going to do ABC. I'll just do it like this, ABC, and I'm going to fill in what I know. AC equals 7, AB equals 11, and angle B measures 25 degrees. Okay, so I have right away, I'm looking for C, angle C. So I will say sine of C over little c is equal to sine of B over little b. And so sine of C, which is what I'm looking for, over 11 is equal to sine of 25 degrees over 7. Okay, so sine of C is going to equal, if I multiply both sides by 11, bam, bam, it equals 11 sine 25 degrees over 7. Okay, and then C is going to be equal to the arc sine of 11 sine 25 degrees over 7. And I know you know how to do that on the calculator, so I'm not going to waste our time doing that. And I'm going to tell you that that is approximately equal to 41.6 degrees. Okay, so let's think about this. So this is definitely a solution. 41.6 degrees is a solution. So we can say C is approximately equal to 41.6 degrees for sure. But we know like 41.6 degrees is about what? Right here on our unit circle. We know right over here there's a corresponding angle, and again this right here, 41.6 degrees, that has the exact same sign. So that could be, the way we find that is we would take 180 minus this. So C could be approximately equal to 180 minus 41.6 degrees. That will always put us in the exact right spot, because essentially, by symmetry, we're chucking out a 41.6 degree angle. We're subtracting it, which is approximately equal to 138.4. Okay, but we still need to check, because it could be that we're in this situation where it really is only one solution. Well, how do we do that? All we have to do is take our obtuse angle and add it to the given angle. So 138.4 degrees plus 25 degrees. And all we have to make sure is it's less than 180 degrees. Why? Because there's only 180 degrees. The sum of all the angles in a triangle is 180 degrees. Okay? So if this is greater than 180, then we would have to throw that answer out, because we can't have two angles that are greater than 180 degrees, because there's no room for a third. So that's how you do it. You always find the second angle by subtracting the first one from 180, and then you test it to see if the sum is less than 180. If it is, we have two solutions. If not, then we have only one. And it might be, wait, how can that be? Well, go back to this first example and look how the leg can swing, keeping the original conditions the same, which were a side of 10, a side of 6, and a 30-degree angle here. And you can see how it can work sometimes, and sometimes it will not work. And finally, find the measure of angle L in triangle KLM. So let's do that. Boom, boom. Again, it doesn't matter how you draw your triangle. Just know that it's not going to be to scale. You can try if you want to, but it's kind of a pain to draw it to scale as you're given the information. So KLM, K measures 56 degrees. LM is 16.8. And KM is 13.5. And they want to find the measure of angle L. Okay, so I would say that the sine of L over little l is equal to the sine of K over little k. Filling in, sine of L over 13.5 is equal to the sine of 56 degrees over 16.8. Multiply both sides by 13.5. Kapow theorem, kapow, sine of L equals 13.5 sine 56 over 16.8. So L is approximately equal to the arc sine of 13.5 sine 56. Again, put all of this in your calculator over 16.8. And I will tell you that that is approximately equal to 41.8 degrees. And so I know that L is approximately equal to 41.8 degrees. Okay. And then I'm going to take, to find my other one, I'll say L is approximately equal to 180 degrees minus 41.8 degrees, which gives me 138.2 degrees. Okay, but I got to check it. So 138.2 plus 56. Well, 130 plus 50 is already 180, plus 8 and 6 more. That is going to be greater than 180 degrees. Well, I can't have more than 180 degrees in a triangle, and I already have more than that with 2. So this answer is thrown out, and this is my only solution. All right. Hope you got that. We'll talk more about it in class. We will end up, as always, going out with ace of base and the I saw the sign. Hope you enjoyed it. I certainly did. And with that, I am out.